I knew it was in there. It's even hidden. Okay, so I wanted to talk about a construct that is a way of understanding models. It's a different way of understanding model behavior than you've mostly seen. You folks have seen, in the course of this boot camp, a couple ways of kind of summarizing model state. Some of those ways provide model state, a summary of model state at a particular point in time. So we saw yesterday, for example, those histograms summarizing model state for different subcomponents of the population. And this evolved every week. We had this histogram shifting, right? And that's fine. But most common, so this was like number of infections, and this was count or probability of falling within a certain bin. This was a bunch of bins, histogram bins. So we saw that yesterday. Another probably the foremost construct we use to understand model behavior is a graph over time. So we have time here, and up here we have one or more variables that are shown. So we might, do a graph of, the number of people who are currently, the number of adolescent smokers in our model. And we see this. Or we might have a graph of the number of individuals presenting for care who are CTAS 3 level or above, or something like that, who have a certain level of severity associated with their condition as judged in the medical care system. So we'll often show graphs over time, and that's very common. But there's another construct that I want to talk about that's actually something called, it goes by the name phase space diagram or state space diagram. And basically it depicts the dynamics of a system in a way that does capture behavior over time, but captures more fundamentally the state of the system. So we might, for example, have a depiction of a system according to the number of individuals who are susceptible, infected, and recovered on this axis. And a given run of the model would proceed at a given point in time. It would have a certain number of susceptibles, a certain number of infectives, and a certain number of recovered individuals associated with it. So each little point here is at a certain point in time. And over time, it will proceed along a trajectory as it evolves. And time here is kind of implicit in the sense that, or it's parameterized. In other words, it might spend a long time here, and you can't really tell from this graph that it does, and then go really quickly here. There's no time axis. What there is a summary of the trajectory in what's called the state space. And this is kind of in a space that you could imagine that is formed by the state of the system. In this case, it's these three things. How many people are susceptible, infected, and recovered. And by depicting this sort of situation, by depicting a system in this construct, you can get some useful insights. You can see how different runs, for example, differ from each other, or how this differs for different parameter values, how the shape of the trajectories. You could examine many trajectories which start at different places, initial locations. So this might be the initial location, and then it swings around like this. And maybe if you start it here, it would swing around, and often it will get to that same place. So here we are summarizing the behavior of the system over time, but with a rather different lens. And this lens can lend itself to some extra degree of understanding and extra ease of kind of labeling things. So here we have one axis for each state variable. Time is implicit. It's movement along a trajectory. And the figures that are shown, like the particular trajectory, is specific to a particular set of parameters. Sometimes this sort of diagram is put in the context of a kind of a field which shows how different trajectories would move over time. But once again, we have susceptibles and effectives. There's no time axis here. Time is sort of occurring as it goes along here. And although these diagrams were generated for a system dynamics model to help us sort of understand a system dynamics model's behavior over time, we can often produce these. We can produce these for any dynamic model. So you could draw out, for example, for your model, the value of one stock and the value of another stock over time as a 2D construct, and see the resulting evolution, or see how it leads to kind of certain cycles within space. So this might be stock 1, and this might be stock 2. Maybe this is, I don't know, maybe this is stress, level of an individual stress, and maybe this is level of sort of some measure of affect or something like that. And you'll see some sort of cycle along here. Or maybe stress and allostatic load, and you'll see some sort of relationship. Often it's really handy to step back from time. These behavior over time graphs are absolutely central to a lot of our analysis, but they're ultimately one sort of lens we can use. And this is another lens that's extremely useful at times. You can find sort of equilibria, you can find situations where it's heading towards some sort of resting point or where it's circling around a point. And very importantly, and this gets to a point I made a couple of days ago, you may wish to label regions of this space as in a certain way. So, for example, Connie and Carol and Jacqueline and I were talking yesterday about the degree to which some of the labeling that goes on within the context of the neurorelational framework might label pieces of state space. For example, we might call this the red zone, and this is, portion of this is the green zone, or what have you. So we might designate areas of state space using certain labels or certain names, and we might be able to understand why we see behavior amongst these kind of labels over time by understanding the underlying state space. For someone like Amin, or someone like Dylan in the past, or Winchell now, who spend a lot of time looking at empirical data gathered via sensors or smartphones, this is a very useful mechanism because you can plot out one set of data, say results from one sensor versus results from another sensor and a third sensor, and you might recognize dynamic patterns here that will give you a clue empirically about what might need to be captured in an underlying model. And it turns out that when you're dealing with complex systems, often through just looking at a few variables, you can get insights into the structure of the entire system because the variables are coupled enough that if there's something going on in some set of variables, it will manifest across multiple variables. And you may recognize aspects of system behavior that you otherwise wouldn't. For example, that system behavior is occurring in a plane and therefore could be represented using two variables rather than three. So these sort of diagrams are very helpful as kind of an alternative way of showing it. I'm not saying you should only want them. Far from it. I mostly operate with these. But there are times I will produce one of these to look at it and kind of better understand what's occurring over here. And often I will put multiple trajectories on this, start it from different points, or vary parameter values and see how that changes the shape of the state space. So state space or phase space is showing how the system evolves over time in terms of its state, in terms of the current situation in the model as summarized by one or more measures. And it's a very useful lens. So that was one thing I wanted to make a remark on. Yes, Scott.
So if I had more than three variables, obviously we can't make an easy graph of them, but could I make like three variable projections
And this is, yes, and this is what I was trying to emphasize. If you have more than 3 variables, even looking at 3 variables will give you great insight about what's going on with the other variables often. Because they're coupled enough, it will tell you a great deal. And so, yes, we do things like that. And sometimes you will find that the underlying dynamics, I mean, I don't want to go too geeky on you, but maybe you felt I did that on day one. Sometimes you will find that the system is depicted in 3 variables, but it is actually evolving along a manifold, a thin area of space, even with respect to the other variables. Its kind of degrees of freedom are constrained, and so it's only operating in a certain region, thin region of that space. And that can give you a better understanding about what variables might be represented in the model, to kind of recast how you're characterizing the model. In general, it can stimulate thinking. Jacqueline.
Still in this question, this is probably more detailed than needed, but if, let's say you did have multiple variables, would it help you to see which ones were more highly correlated, so that way you could, if these were highly correlated,
exactly.
Don't put them both in there, put in one of the other ones.
Exactly. And particularly if you're kind of looking at, on the one hand, data, let's say data from sensors, right? And the other hand, a model's results. This might really help you understand, okay, to what degree do they jibe with each other in a way that's going to be an alternative characterization from what you get with a behavior over time graph. It may be that you see actually the underlying structure is very similar, even though one is playing out over longer periods of time and one is shorter. Maybe that's just a matter of how quickly time goes. If you put them into a diagram like this, you might actually find they're quite close to each other, for example. Or as you say, you find certain things are so correlated that you could, you might want to choose a different way of representing the system using just two variables or a smaller number anyway, and be able to summarize it. So it's a very useful construct. And in general, I tend to think of when we're thinking about a system's dynamics, underlying dynamics, it's very common that we might characterize portions of the space using certain terms, like this is an endemic state or something, and it's referring to kind of a portion of this space where a system is exhibiting certain behaviors. One very important thing that I haven't emphasized, but yeah.
This is a particular run under a certain set of parameters that's characterized by some of the variables within the model. You also do a set of runs and then
totally.
Be the
totally. Precisely. So this space is not specific to a run. I mean, this space could be depicted for any run, and we could put in blue, one run, red another, green another, and we do exactly that. Is sort of displaying multiple ones. One of the most powerful things is, or one of the most profound things is that when we're dealing with these nonlinear models, often what you get is different. Again, I got to be careful. Things that excite me don't necessarily excite you, but you get different basins of attraction. So you get different regions that kind of pull the system towards them. And so, we think about this. I see this all over the place, in daily life. So projects that can go bad or go good. Often with vicious cycles, this is what happens. You can have the same project, and I've seen this happen, unfortunately. It happens a lot in software development. The same project going well, group of people, really high morale. They're really committed, very low turnover, very little documentation needed because they've been working together for so long. They have so much of it in their heads. They're communicating very efficiently, high-quality code base, high-quality results. Lots of people want to join the team because it's really up and coming and going good. And then with managerial dysfunction, you can see that same project like go to hell in a handbasket. You can see the same people be in a miserable state. There starts to be higher turnover. It requires heavy documentation because people are walking out the door with all sorts of knowledge. That makes it even more undesirable. They have a hard time hiring new people, and they spend a lot of time training the new people they hire only to see them leave. And the project goes in a different way. And we talk about those as different basins of attraction. It's like two different regions. Water on one side runs down in one and goes down to an area where you're constantly fighting fires, and so the other side. Jeff talks to me about dementia wards being similar, and I mentioned that in my first day, that, there's the same dementia ward under the guidance of the right nurse who's got a real subtle handle on the sort of patient agitation and so on, can be in a great state, or with the wrong situation, it tips, and then it goes into a different basin. And so it is with these things. Often you'll find there's a dividing line, and, if you start on this side, you'll spiral over to this place, and otherwise it spirals over here. And those are associated with tipping points, sort of tipping regions, and you can spot those by showing different runs of your model with different parameter values. You will see them going to these different phases, as it were, with totally different situations, each stable, each potentially with lock-in. It's harder to get out of it once you're in it than it would have been to prevent it from getting in there. And you will see that depicted in a diagram like this in a way that you would not using a behavior over time graph. Yes, Scott.
So just using that for this conceptual perspective, if I have empirical data of a process I want to model, I see this type of behavior, which is quite literally it's all going to one point all the time, or multiple points. This would example be saying I need to have balanced loops because that's exactly the type of structuring this dynamics that would create this type of behavior, etc.
But again, I want to emphasize, even though this is widely undertaken with system dynamics models, in fact, system dynamics packages commonly include a tool for directly creating this for the last run, for example. It's something that we may do to summarize the state of an agent-based model. Agent-based models, or discrete event, or hybrid model. Agent-based models, hybrid models, discrete event models have lots more moving parts. The full state space is very large, but we can summarize the state space in terms of count of people who are in different conditions, or the state of a given person, or what have you. We can still very fruitfully use this construct. And AnyLogic does provide the tools for doing this with XY plots, with plots that can be scatter plots or connected with lines. So you can actually create this quite readily. And in fact, there's this construct which some of you will see probably later today in a parallel lecture of mine, which is called the data set, that allows you to keep XY values and, for example, plot them on an XY plot. But this is a very useful way of depicting situations, and you may spot things like multiple basins of attraction, multiple sort of attractors that can be very useful at an operational level and sort of cluing you into dynamics. Okay? Very good. So that was just one set of comments on phase space. Any questions on that? Okay. Great. So I'm going to just record